Hi everyone, I'm happy to introduce you to the ResNova project. This is a newly proposed experiment for the investigation of neutrinos from astrophysical sources, and ResNova plans to use an array of cryogenic detectors made of archaeological lead. And the scope of ResNova is mainly focused on the study of supernova neutrinos. So in one slide, why supernova neutrinos are interesting. Well, we know that supernovae are among the most energetic events in the universe, where almost the entire beating energy of a star is released as neutrinos. And so if you are able to detect these particle and messengers, we might be able to infer information about the core physics and the reaction that drives this explosion and high energy cosmic event. Unfortunately, our knowledge is mostly based on simulation, given the fact that we were only able to observe one supernova with underground instrumentation. And so really having the possibility to detect the next supernova will be a game changer for our knowledge. Here we show one-dimensional hydrodynamical simulation of a 27 solar masses progenitor star exploding at 10 kiloparsec from us. We show the neutrino luminosity and the average neutrino energy as a function of the time after, say, the start of the core collapse. And with different colors, we represent the different neutrino flavors. Here, nu X stands for muon and tau neutrinos. And as we can see from these two plots, mu and tau neutrinos are among the most abundant and most energetic neutrinos in this event. And so having the possibility to detect the full composite neutrino signal, so not only electron neutrino and antineutrinos, can really be a breakthrough in neutrino, low energy neutrino astronomy. And this is because the currently running experiments are mostly sensitive only to electron neutrinos and antineutrinos. ResNova plans to use the coherent elastic neutrino nucleus scattering as the detection channel, and this has some key features which makes it really an interesting process to be exploited. So it is a neutral current process, so in this way we can be sensitive to the full composite neutrino signal. It has extremely high cross section, and if we compare it with the electron scattering, then we see that this is many orders of magnitude higher, as shown in this plot where we shown the interaction cross section as a function of the energy of the incoming neutrino, and this dashed gray line is the electron scattering, while the solid colored line represent the cross section for the coherent elastic neutrino nucleus scattering cross section for different element. In addition, this is a thresholdless process, so there is no kinematic threshold involved, and ideally we can be sensitive to the full neutrino emission. If you look into the details of the equation that describes the cross section, which can be easily derived from standard model basic principle, we see that this depends on the form factor, the nuclear form factor of the target nucleus, so the size and the charge distributions of the nucleus, but also on the electroweak charge square. And this is a function of the Weinberg angle, and most importantly, of the neutron number. So the higher will be the neutron number, the higher will be the cross section. And this is the reason why we see here in this plot that lead is the element with the highest cross section. And then last but not least, the cross section square with the scale with the square of the neutrino energy, scale with the neutrino energy square. And this means that the higher is the neutrino energy, the higher will be the cross section. And so this makes really this process ideal for the detection of supernova neutrinos, given that these have high energies. And but let's have a closer look on lead. So lead is really very interesting, as said, because it's the only element of the periodic table that ensures simultaneously the high cross-section for high sensitivity and high nuclear stability. And this is extremely important if we want to achieve a low background level, given the, let's say, the fact that we want to be sensitive even to really weak neutrino signal from far away supernovae. The signal that we were expecting to observe is a nuclear recoil on the target induced by the neutrinos, and as a rule of thumb for lead, we can say that a 10 MeV neutrino will induce a nuclear recoil of 1 keV. And so if this channel is it's interesting when the interaction between the neutrino and target nuclei is coherent, and this happens when neutrino have energy up to 30 MeV. And so if this is the case, then really lead can be considered as an ideal target for the investigation of the neutrinos. And if you look at the energy spectrum of supernova neutrinos, as shown here, the average neutrino spectrum, we see that up to 30 MeV, we can detect, let's say, almost, I'd say, 100% of the neutrino emission. So really, and it's also an efficient target for this type of investigation. But then how are we able to include lead in a target material? Well, ResNova, with ResNova, we want to include it in a cryogenic detector and exploiting the same techniques that are developed for the neutrino stable beta decay sector and the direct dark matter sector. And especially we want to take advantage of the low background techniques and the scalability to large volume, as demonstrated, for example, by the Quarry or the QB0 experiment, and also take advantage of the ultra low energy threshold achieved by dark matter experiment as the CREST experiment, which is able to achieve an electron volt scale energy threshold. And so given this aspect, we really think that these technologies can be suitable for our purposes, especially because if our scintillator, lead-based scintillator, is also an efficient scintillator, low temperature, then we can even perform a particle identification and reject possible background sources which are not nuclear recoils. And however, suppressing or reducing background in cryogenic detector is quite difficult, and it's shown in this measurement that we perform where we run a lead tungstate crystal, so containing lead, of 0.5 kilogram and produced from low background lead. And in this scatter plot where we showed light yield as a function of the energy deposited in the crystal, we see an overwhelming background both of alphas, but especially of beta gamma background. And this is due to the fact that the lead that we used was low background lead, but was shown still an extremely high concentration of lead-210. This is radioactive, as a half-life of 22 years, and has a Q value of 60 keV. And so really around our region of interest, since we are looking for nuclear recoils at the keV scale. So we can really overcome this issue of lead-210 only when archaeological lead is used. In fact, this is old enough such that all the lead-210 is completely decayed after 2,000 years. And actually, we were able to measure, to establish a limit on the concentration of lead-210 in archaeological lead, limits lower than 1 millibecquerel per kilogram. So really almost more than 5 orders of magnitude lower than the one of low becquerel lead. In addition, archaeological lead ensure a negligible concentration of uranium and thorium nuclides at the same level of the of low background lead. So we have defined what type of lead we'd like to use, what type of technique. Let's have a look at how we should design our experiment, how big should be our experiment. And this plot will show the number of neutrino events detected above threshold for different energy threshold, different colors, as a function of the detector linear dimension. And ResNova, the first phase of ResNova, which we would like to install it at the Grand Sasso Lab, will have a total volume equivalent to a cube of 60 centimeter size. So really a compact and small scale experiment, centimeter scale, with only an energy threshold of 1 keV, so not prohibitive at all. We can detect, depending on the supernova model, let's say about 30, 40 neutrino events from an event at 10 kiloparsec from us. And so really, a centimeter scale experiment that can be easily fit inside a commercially available cryogenic facility. It has a rather large mass, almost 2 tons. This is due to the fact that lead tungstate is rather dense material. And obviously, this will not be a monolithic detector, but will be a modular detector of 500 single modules. And later, we will see also the advantage of this modularity. And as said, we'll have an energy threshold of 1 kV. So let's have a look at which will be the detector response, how a supernova event will look like in ResNova. And here is the detector country rate as a function of the recoil energy for two different supernova model, a failed core collapse of 40 solar masses and a 27 solar mass conventional core collapse. And we can be sensitive to this signal only when archaeological lead is used. And because commercial lead, as shown in this gray area, it's as high as the signal. And once archaeological lead is used and our sensitivity increases, it can even push further when particle identification techniques are set in place and when we are able to reject the full beta gamma background, as we are left with only nuclear recoils. Our region of interest lies between the energy threshold, in this case 1 keV or possibly lower, up to, in this case, let's say 30 keV. ResNova is a modular detector, and so this is extremely important because we are expected to observe many neutrino events in a short time, and we don't want to be affected at all by pile-up, as may happen in monolithic detectors. And given the fast time response, 100 microseconds for each detector and the large number of modules, 500, well, we can really identify the different neutrino emission phases while the supernova is occurring. So we can identify easily the neutronization, accretion, and cooling phases for this the same model as shown before. But in addition, we can really, let's say, pin down the model which is driving the explosion, as well as the mass of the progenitor star. This while running a small-scale experiment. So we said that the signal, we can observe it quite, let's say, easily, but how about the backgrounds? Well, we have performed some Monte Carlo simulation where we have simulated different background sources in the experimental setup, in the detector volume, in the all the ancillary components, the detector holders, the copper detector structure. We have not considered at all any external video to the setup. And here we show that the background rate as a function of the detector multiplicity. Well, detector multiplicity means how many detectors are triggered by one single event. And as we can see, the background rate, which is represented by the bars, it's decreases with the increasing number of multiplicity. So it's difficult to imagine to find some events that with background event that is able to trigger many detectors at the same time. And this is a key aspect because we are expecting to observe a large number of neutrino events in a short time, and which means that we'll have a high multiplicity signal, and the signal here are represented by the markers, while we will have a small background, given the fact that background with high multiplicity are expected to be extremely small. And so this is really an advantage of this modular detector. So knowing, being able to estimate the possible background level and the signal, we can compute the signal significance. And in ResNova phase 1, we show here the signal significance as a function of the distance at which the supernova is occurring for the different two models. The width of the bands represents these two extreme cases where we are able to perform a full particle identification technique, and so reject all possible background sources except for nuclear recoils, and in the lower side of the band where we are not able to perform any particle identification. So in our region of interest, we will have nuclear recoil and electron gamma interaction. And we can see that with such a small scale detector, so 60 centimeter cubes, we are able to explore the full Milky Way galaxy and reach out till the large and small Magellanic Cloud. And this while being sensitive to new X neutrinos. So really, ResNova can be considered as a complementary experiment to the current running one, providing unique information. But how about the feasibility? Well, we were able to operate the first prototype detector, a small-scale crystal operated above ground, 16 gram, produced by from Archaeological Lead, and equipped with a transitional sensor of the same type developed by CREST. We were able to achieve a baseline energy resolution of 6 electron volts, which translates in a nuclear recoil threshold of 300 electron volts. So well within say our expectation. And so really, this is a small-scale proof of principle of this technology. We still need to prove that the background level that we want to achieve, we can achieve it, but for this we need to run a large mass crystal underground, and this is what we are planning to do in the coming months. So coming to the conclusion, ResNova is a new proposed experiment for detection of supernova neutrinos. It will be the first centimeter-scale neutrino telescope. This thanks to the high cross-section of coherent lasting neutrino nuclear scattering and the low background level that we can achieve with archaeological lead. The technology that we will adopt is a well-established technology, and it's already exceeding our expectations, achieving a threshold of 300 electron volts, and ResNova can really provide complementary information to the currently running experiment thanks to the sensitivity to the full composite neutrino signal. So thank you very much for your attention.